especially for those who were under me in S&P. Okay, that's the first time that you heard about maxima and minima. Okay, so again, what's a maxima and what is a minima? We first heard this when we were dealing with parabolas, right? Yes?
Yes,
Yes or
teacher.
no?
Yes,
Yes,
teacher.
teacher.
Okay. So if you have a parabola or if you have a graph, for example, and we have a curve like that, this curve or turning point over here, we call that one as your maxima, right? Okay. And we can relate it as to the highest point, okay, the highest value that a certain function can reach. That's the highest value that a certain function can reach before it turns down. Okay, if you have another one like this point over here is another turning point and it's lower than this one, so you call this one as a minima, okay, a minimum point. Okay. However, this is now pertaining to graphs. So how do we relate your maxima and minima to real world situations? Okay. So if you will be working in the field as any, let's say, maybe an engineer, okay, let's just focus on engineer. Okay, so if you will become an engineer in the future and you will be working in the field, be it you are a mechanical engineer that you are working with engines or building your own engine, or industrial engineer, wherein you are going to be dealing with customers and selling products like big machines, or production engineer, wherein you will be the one in charge of producing, making stuff, okay? Be it as an electrical engineer, what, electrical or electronics engineer, okay, and the stuff. You will be producing something. You will be making something. And when you make something, you make an item or an object or a tool, you need materials. Correct? You need raw materials to make it. Okay. For example, we are working in a plant that produces containers or metal containers like this. Let's keep it simple. Okay. So let's say that this is made up of aluminum container. Okay. Right. So basic container like this, if this is now made up of, let's say, aluminum, does aluminum come in this shape? When you're going to produce or make, does aluminum come in that shape?
No.
Yes or no?
No.
No. Okay. Usually aluminum is going to become in big rolls. Okay. Very big rolls and sheets, flat sheets of aluminum like that. Okay. And we are not talking about A4 size. We are talking about a very big, a very long roll, okay, of aluminum. Let's say about 4 meters or 2 meters by 100 meters. Okay, so that's a very long sheet. So that would be 4 meters by 100 plus meters. Okay, now the thing here is, how do you make this? How do you make this product? This is now your knowledge in geometry comes in. How do you make this product? You need, at least you need a rectangular piece, correct? Right, you need to cut units, right? Obviously, you need to have, yeah, and then you're going to get one piece, and then how will you shape this into this? Come on. It was an exercise when you were in SD6, I think, SMP as well. So, how do you make this shape out of this?
Like those.
Okay, first maybe make your measurements here, height, right? Okay, then you cut it like this. Wherein this is now your fold lines over here, right? The point is, you are not going to use all of the material. This part is going to be cut off, right? You need to cut off that part, and then you need to fold this one and then join them together to form the seams, and that will now be your container, right? Clear? So technically this one goes to waste, right? Yes or no?
Yes. Yes.
That is
Yes.
now going to be waste. Now, if you are now going to be working in a company, what do you need to do to ensure highest profitability and highest yield, meaning highest number of items made? Are you going to maximize waste?
Minimize.
You need to minimize waste. Minimize waste and then maximize usable area. In this way, if you're going to maximize your usable area and minimize waste, then that means you will be saving more of this material and it will save money for your company. You understand what I'm saying? Okay, so you need to know what parts you need to maximize or what measures you need to have in order to maximize the use of this material so that it will be beneficial to your company. Okay, so you can just imagine you need to cut these parts out, right? You need to cut these parts out in order for you to be able to form your shape. So the thing here is the question is what measure? What is now the measure that you're going to apply for the length and width of this container in order to maximize this item that we have here? So that's the question that we need to answer. Okay, so basically this is a question that is suited for your maxima and minima problems. However, we cannot just jump directly into this. We need to understand the basic concept on how to do the math behind it in order for us to be able to apply. Okay, clear?
Clear, teacher.
Okay, so here we are now going to be learning first the different components of your maxima and minima before we will be able to apply them in real world situations. You can find the lessons on page 46 of your textbook. Okay, so our new lesson is your maxima maxima and a minima, okay? Maximum value or minimum value. Okay, so starting off with the first component, one higher order derivatives. Okay, so we have been dealing with derivatives for the first half of the year, and you already know most of it, okay? So if we have here, let's say, y equal to 2x squared, y equal to 2x cubed, let's do cube, minus 3x squared plus 8x minus 12, okay? If I want you to find here your dy per dx, okay, dy dx, what will we get? As quickly as we can. Dy dx is
6x squared minus minus 6x plus 8.
okay, good. So that is now 6x squared minus 6x plus 8. That is now your derivative. However, this is what we call your first order derivative. Okay, it's the first order derivative. Why do we call it first order derivative? Since we took the derivative once. That's why it's called first order derivative. Okay, in reality, the correct notation here is d raised to 1, d raised to 1y, dx raised to 1. Okay, that's the first order derivative. Okay, so with this one, instead of writing it dy dx always, dy dx is equal to like this, we can actually shorten the notation. Okay, we can shorten the notation using, since that is now y, we can write it as y prime. Okay, this is now named as or read as y prime. Okay, that's y prime, this symbol. So this one can be notated shorter as y prime is equal to 6x squared minus 6x plus 8. Okay, clear? So that's one apostrophe over here. That means it's the first order derivative. Okay, are we clear on this?
Yes.
Yes or no? Okay. Another way of notating, what if we are given a function? It's not written in y form, but it is given as a function. F of x, for example, is equal to 2x cubed minus 3x squared plus 8x minus 12. So how do we write this as the first order derivative using f of x? Okay, to write it in the first order derivative in function form, we put the prime there before f or after f. So this is now named as f prime of x. Okay, f prime of x is now equal to the same thing if we have this one. So 6x squared minus 6x plus 8. Okay, f prime x, or first derivative, is this. So since we are now discussing about higher order derivatives, okay, and this is just the first order, first order derivative, same, this one is also first order derivative over here. So when we talk about higher order derivatives, okay, this is now the next level of the derivative after the first level. Okay, so basically it's just saying that you take the derivative of the derivative. You get the idea? So if I'm just going to copy this one over, okay, so if I have, let's say, y equal to 2x cubed minus 3x squared minus 8x minus 12, we got dy per dx is equal to 6x squared minus 6x plus 8. And then what we need to do is to get that, okay? We get this and we take the derivative again. So d dx, d dx of this. Okay, so to notate it properly, this is now going to give us d squared, that's d and d, okay, right? D squared per, this is as a whole, dx squared, okay? Dx squared y equal now to, take a derivative again. So this is going to give us
12x minus 6.
x minus. So this is now called, since that's 2, we took the derivative 2 times. Okay, we took the derivative 2 times. This is now known as your second order derivative. Okay, second order derivative. Does it stop there? Basically, no. Okay, depending on the use later, we might go on higher, second, third, fourth, or fifth derivative, depending on the application. And we will learn the applications later. But for now, it's just for you to understand how to get your higher order derivatives. So if I'm going to ask you to find d3 y dx cubed, that means what? We need to get its third order. From where? From here, okay? So it will end up, third order is going to be simply 12. Okay? Is this one clear?
Yes, it's clear.
Okay, so again, this one is now your third order. Okay, it's easy to understand. Now, it's bulky to be keep on writing like this, dy dx, d squared y, dx squared, d cubed y, okay? So we can shorten our notation either by using this or this, okay? To shorten it, okay, so let's play y. That means this is going to be y prime. This one, first order, second order will be y double prime. Third order is going to be y prime prime prime. Okay, third order. Okay. How about fourth order? The fourth order, it's prime, prime, prime. It's too much, okay? So if you go higher order, it is now going to be y dot 4, okay? Y dot 4, y dot 5, y dot 6, okay? But this is now for very, very, very advanced mathematics. Even me, I only know the use up to the third order only. I do not know the use of the fourth, fifth, sixth, seventh, eighth order. Okay? If I will get a doctorate in mathematics, maybe I will be able to understand what is the use of this. But for now, it's safe to say until 3 is okay. Clear? Now, in function form, that is now f of x That's now f prime of x. Same. F prime prime of x can also be f triple prime of x. Okay, third order. If you want to go higher than this, you can say f of n of x. Okay, f of n of x, it's not cube, f cube. So if you say f5 of x, this is not saying that it is now going to be f, the function raised to the fifth power. Okay, no. This is now the derivative, okay, the fifth power derivative of the function. Clear?
Clear, teacher.
Okay, so these are just some notations because I do not, since we are doing your derivatives like this, I do not want to be keep on writing it this way. So if I will ask you to find, okay, for example is, if I have here f of x is equal to 2x raised to 4 plus 7x cubed plus 3. And I want you to find f prime prime. Oops. Ah. So that means, what are you looking for? You're looking for
The second order derivative.
okay, you can just call it the second derivative. It's easier to say. So second derivative, the answer will be, you can start with f prime of x is now going to give us
8, 8x cubed plus 21x squared.
okay, plus our f prime prime
24x
give us
squared plus 42x.
Done. Okay, easy, right? Easy to understand.
So far, yes.
Okay. We will discover the use of it later in connection to maxima and minima. Okay, but for now, let's do some practice examples on this. Get your textbook, open it to page 47. Okay, and do try it yourself, number one, page 47. So it is written in f of x. Ah, no, it's written in y. So it will be y. What's that? It's asking you to find the. Try to. Are you there in the textbook?
Yes.
Page 47. Try it yourself, number one. So you're given y equal to x to the fourth. X to the fourth minus 2x cubed plus 6x squared minus 7x plus 1. And you are now going to find y second derivative. Okay, y double prime is what?
I got 12x squared minus 12x plus 12.
12. Okay, let's see. So y prime is equal to 4x cubed minus, that is now going to be 6 minus 6x squared plus 12x. Okay, and then y double prime is now going to be 12x squared minus 12x plus 12. That's as easy as it goes. Okay, okay, so that's it. Okay, I think we still have a lot of time, right? We still have 10 minutes. Okay, so how about if we have here number 2? Okay, so we have here the second question, and I want you to find f prime of 3 and f double prime of 3. Okay, meaning find the value of the first derivative when x is 3. Find the value of the second derivative when x is 3. You understand the meaning of this?
Yes, teacher.
Yes. Okay, so let's work on it then. So first of all, from here, we need to find f prime of x. F prime of x will be what?
Wait.
This is in multiplication. So we need to apply your rules. Product rule. Product rule is copy the first.
U
That's
dv
a and b, right?
dx. Yeah.
Okay, u dv. Derivative of this, that will be? Okay, let me just write it first in exponential form, the radical. Okay, f of x is now equal to x times x squared plus 16 raised to 1/2. Exponential form. So f of x, f prime x is equal to, copy the first, chain rule of this one.
Half times x at half times 2x.
1/2. Derivative first. Okay, 1/2 times x squared plus 16 raised to negative 1/2
Then times
multiplied by derivative of what? Derivative of
2x
2x. Good. Okay. Then plus
plus x squared plus 16 raised to half times 1.
this one. Copy the second one. X squared plus 16 raised to 1/2 times derivative of the first, which is now 1, or simply just leave it like that. Okay? Simplify. F prime of x is now equal to
X squared over
1/2 and 2 will cancel, x squared. So
x
x squared over
x squared plus 16
x squared plus
to
16
half
raised to 1/2 plus
plus x squared plus
squared
16 raised to half.
plus 16. Okay, raised to 1/2. Basically, we do not need to write it in simplest form because we are still going to evaluate it when x is equal to 3. Okay, so get your calculators and apply it here. What do we get?
34 per 5.
34 per 5. Okay, 34 per 5, or in decimal, So f prime of 3 is equal to
6.8.
34 per 5. 34 per 5 or 6.8. Okay, so there, that's the first one. How about the second one? Second one is we need now to get f double prime of 3. So we have f prime already over here. I'm going to use the simplified version with this one on top. So f prime of x is now equal to x squared. This one is going to be on top. So x squared plus 16 raised to 1 half plus x squared plus 16. Oh, sorry, that's negative 1 half. This one is 1 half. Okay. So f double prime,
So it's
chain,
2x.
yeah, chain
Yeah.
rule here again. That will be copy this, derivative of that.
Yeah.
So x squared, derivative of this, times negative 1 half,
Times x squared plus 16 raised
x
to negative
squared
1.
plus 16, negative,
Negative 1.
negative 1, no?
Negative 3 per 2.
Negative 3 per
Yeah.
2, kali
2x.
2x plus, where did we start a while ago? Copy
Then we copy the second.
this one now. Okay, copy this one. X squared plus 16, negative 1 half times 2x. Okay, plus,
Half
plus
times.
this one,
Yeah,
half
times
times
x squared plus
x
16
squared
raised to
plus
negative 1
16,
half
negative 1 half,
times 2x
then
times 2x.
times 2x. Okay, what can we simplify?
Half and 2x.
Ini negative, right? Negative times this one. So negative x cubed. So f double prime of x is equal to negative x cubed multiplied to what?
X squared plus
X squared
16
plus
raised to negative 3 per 2.
negative 3 per 2. This one, I think, oh, we can, right?
No, we cannot cancel. There's no 1 half in here.
So let's
Just leave that.
let's just x squared plus 16 raised to negative 1 half, then plus ini cancel x times x squared plus 16 raised to negative 1 half. Negative 1 half x squared plus 16, x squared plus 16, we can combine this one. Ah, we got the 2x. We have 2x over here. So there should be 2x in front. Sorry. Okay, basically we have here f double prime of x is equal to negative x cubed times x squared plus 16 raised to negative 3 per 2. 2x plus x is 3x plus 3x times the same factor over here, x squared plus 16 raised to negative 1/2. And you just need to evaluate this at x equal to 3. Okay, so we only have less than a minute left. So you should arrive at f double prime of 3 is now equal to 198 per 125. Okay, clear? We continue on this by next meeting.
Okay, thank you,
That's
teacher.
it for today. Goodbye, everyone.